The following video explains why Earth's shape, when viewed from space, will show a visible curvature. This is not a work of fiction. It is a result of months of work involving physicists from Brazil, Germany, and the United States who hold master's degrees in physics, astrophysics, and cosmology, and also masters in theoretical physics. This is a simple recital of fact which transcends the most elaborate fictions ever conceived. The information to come is diametrically opposed to the assumptions and explanations put forth by both the flat Earth community as well as established scientists and physicists. Although the majority will be pleased to label us crackpots, flatheads, idiots, and fools, it was the fool who threw black dirt into an open wood fire and through such foolishness established the value and purpose of coal. Socrates, the ancient and profound philosopher, was considered mad by the majority of his time. We may read about the strangeness of Robert Fulton, who harbored an insane idea of harnessing steam for the propulsion of boats, or Benjamin Franklin's insane tampering with the elements by catching lightning with his stupid key in a kite. The eccentricity of Thomas Edison is recalled with his particular insane notion of holding powerful electricity in a fragile glass bulb. Alexander Graham Bell's plodding perseverance provided our telephone, and the madness of Samuel Morse, who was guilty of the wild claim that messages can be sent throughout the world without the sound of a voice. The entry is hardly dry on history's page recording the Wright's folly. Such a term described the majority's opinion of Orville and Wilbur Wright. Yet while the normal majority ridiculed the new enterprise beyond their understanding, the Wright brothers threw tradition's restrictions to the winds and navigated the first crewed airplane over Kitty Hawk. The new and unknown is always fearful to the majority. The fears attending to normal pursuits within an established social pattern may be dispelled by one means or another, but the fear of that which is new and unknown, and which is beyond the conditions of the ordered pattern, must disturb the conforming majority. Human nature demands that beliefs acquired must be cherished and protected, be they ever so incomplete and faulty. My truth is the truth, so say we all. Thus, like a porcupine projecting its quills and sensing possible danger, the majority become automized to throw against the new and unknown the oral quills of skepticism, cynicism, and ridicule, without even hearing the value inherent in the new. They fear that the new might encroach upon or upset cherished beliefs. But the fearless experimenters and pure scientists, the crackpots, visionaries, dreamers, and madmen, with their indomitable spirits who build civilization, are nourished by a creative nectar too potent for the normal majority consumption. The common theory as put forth by NASA is that Earth's visible curvature, as seen from space, is the actual curvature of the Earth, thus proving that the Earth is a sphere. And if you can see the curve, then you will know that the Earth is a sphere.
So tell me, Neil, is the Earth flat?
We have video from space of the rotating spherical Earth. The Earth is round.
Thank you for joining us on this episode.
No, B.O.B.'s on the gram talking a lot of this stuff, and he's actually, he's got a GoFundMe. He's trying to buy a satellite to take his own pictures to prove.
So before you do that, why don't you consider joining the Planetary Society? We will have a satellite. Join the Planetary Society. We will have cameras that will take a picture of the Earth, and you can decide for yourself. Not a conspiracy. Come to Cape Canaveral and see the rocket launch.
After all, you can just go to Cape Canaveral and watch a rocket launch and you should be instantly convinced that the Earth is a sphere. Now, both of these men have assumed that there is no visual distortion for the viewer outside of the atmosphere who's looking back down to Earth, which is not only a physics fallacy but also a violation of Newton's third law: for every action there is an equal and opposite reaction. This will be explained thoroughly in the video. Most flat Earth theorists will say that every photo and video from space is taken with the fisheye lens, and that the barrel distortion of the fisheye lens creates the curvature seen. This assumption means that the curvature is only seen in photos and videos, but would not be seen with the naked human eye. Additionally, this assumes that if a regular camera without a fisheye lens was used in space, that you would see a perfectly flat horizon. So we can see that Neil deGrasse Tyson, Bill Nye, and most flat Earth theorists all agree that there is no visual distortion for the viewer who's outside of the atmosphere, who's looking back down to Earth. Now again, this is a physics fallacy, and we'll come back to explain this in detail. But first, let's look at a history of stratospheric photographs to immediately debunk both of the previously mentioned theories. Humans and cameras did not reach the stratosphere until 1931, when Auguste Piccard became the first man to reach an altitude of 51,775 feet. Looking through his porthole, he reported seeing a flat disc with an upturned edge. A downturned edge looks like this, and an upturned edge looks like this. Given that Piccard's porthole was pointing approximately 45 degrees above the horizon line, we now understand why he reported seeing an upturned edge. Now we know why we find Piccard studying the physics of light traveling through a prism after his historic balloon journey, and in this video we'll also perform experiments with prisms. About 15 years after Piccard's balloon flight into the stratosphere, the V-2 rocket became the first man-made object to travel into space by crossing the Kármán line on June 20th, 1944. Just a side note, the Kármán line, or the edge of space, lies at an altitude of 62 miles, which is still in the atmosphere, the thermosphere specifically. And to truly leave Earth's atmosphere, you would need to travel another 6,138 miles, where the exosphere merges into the solar wind. But the V-2 rocket did reach altitudes up to 100 miles, and the US had captured enough V-2 hardware and personnel from the Nazis to build approximately 80 of these missiles. Therefore, 80 experiments were performed between 1946 and 1951, and as a result, the first photos of Earth from 40, 70, and 101 miles altitude were taken. The photos were released, and the distance to the horizon at an altitude of 70 miles was only about 350 miles. This would mean Earth's radius is only around 2,000 miles, and this is a serious problem. This has been discussed in further detail in my V-2 rockets exposed video found here on my channel. But the curvature seen is an optical illusion caused by the atmosphere, and will be explained in this video. The photos do show a curve, and this is expected because the first pictures were taken straight down, and subsequent photos were taken at more and more oblique angles. All of the photos were taken with the camera pointing below the horizon line, thus the downturned edge. Remember, Piccard's porthole in the view of Earth was aiming up and above the horizon, and therefore the upturned edge. So the V-2 rocket photographs showed that the Earth's horizon is convex or downturned, and it's known that the camera was pointing down and below the horizon line. Next, let's look at the video from the 1964 NASA balloon. In this video, the Earth's horizon can be seen first as concave or upturned, and as the camera rotates back down towards Earth, we will then see the round or convex horizon. At the beginning, the camera was pointing above the horizon line, and later in the shot, the camera has rotated so it's pointing below the horizon line. This video shows both a concave and convex horizon without a fisheye lens. Moving forward to the Apollo missions, the cameras which took photographs of Earth used RCU camera brackets, which did not allow the camera to rotate along its x-axis. They were locked into place, as almost all NASA cameras are. The same can be said for the NASA STS missions, but the Earth shown in those videos is hardly believable. Moving forward to NASA's current work with SpaceX and the GoPros being used, we can see the effect clearly. Earth's horizon will begin with an upturned edge, then it will be flat, then it will have a downturned edge. And once again it will go flat, and now an upturned edge. This is also seen in the Red Bull Stratos skydive from space, when Felix jumps out of his capsule, the horizon is concave, then it goes flat, and then convex. Although this will be commonly blamed as barrel distortion caused by the GoPro, we'll prove that to be false. Let's look at the U-2 spy plane video in which we can see that a non-fisheye camera is being used. And we can measure a perfectly flat artificial horizon line inside of the cockpit. If a fisheye lens or a GoPro was being used, this line would be curved. There is no fisheye lens barrel distortion in this video. When the camera is pointing above the horizon line, Earth will take a concave shape with an upturned edge. When the camera is pointing below the horizon line, Earth will take a convex shape with a downturned edge. And when the camera's X rotation is at 0 degrees and perfectly aligned with the horizon, Earth's horizon will be perfectly flat. We can confirm in this video from flat Earth theorist Rob Skiba in his high-altitude balloon launches, which have both a standard and a fisheye camera on board. Although the cameras do not aim above the horizon, we can see the curvature of Earth increases as the camera points downward, even on the non-fisheye lens. This convex to flat to concave transition of Earth's horizon can be found everywhere from NASA to SpaceX, an iPad case company, GoPro cameras, independent parties, flat Earth theorists, and basically anyone who has taken a camera above 100,000 feet. Now let's explain the science and physics behind the visual distortion, which is a function of the lens and caused by light refraction in the atmosphere. First, it's important to study how human and camera lenses produce their image. Let's peer into the workings of the eye. The reflected light of the world enters through the crystal transparency of the cornea, aqueous humor, lens, and vitreous humor to project onto the photoreceptors of the retina, whose impulses converge on the optic nerve and are sent to the brain to be transfigured into an image. Continual adjustments to the pupil and lenses regulate the entry and focusing of light. Here are a few observations to consider concerning the human eyeball. The human eyeball is a light-reading device that can only form an image if light can reach and enter the pupil. The human eyeball is a sphere and the pupil is a perfect circle. Light waves entering the cornea may only enter with the shape of a circle. Anything below the horizon, which is visible, takes its true form and shape, but when something is too far away, it becomes a dot or a circle and disappears into what is known as the vanishing point. Everything that is above the horizon, the sun, the moon, stars, and planets, are all perfect circles, and they're also very far away. In fact, if they were on the surface of the Earth, they would be so far away that they would have disappeared into a circle known as the vanishing point. Are you positive that you're seeing the true nature of the celestial objects in the sky? Or is there some illusion from your fallacious light-reading eyeball? Because human and camera lenses are light-reading devices, we must consider the path which light has traveled before it reached our cornea to produce the image that we see. The refraction of light can create many different interesting optical illusions. Suppose we change the shape of the lens. Let's now return to our original shape. Suppose we change the location of the objects. The image can be either right side up, or it can be inverted upside down. A beam of light is composed of particles called photons. Photons are very different from the particles that matter is made out of. The image which you can see is developed from light photons, and it is not an exact translation of the physical matter around you. The speed of light through a vacuum is the same for all observers. But light slows down when it tries to pass through certain materials such as glass, water, and air. The velocity of light decreases with increased density of the material it's traveling through. When a wave enters or exits a material at an angle, the left side and the right side of the wave will cross the boundary at different times. The greater the angle, the greater the difference in time when the left side and the right side of the wave will change their speed. This causes the wave as a whole to change direction both when it enters and when it exits the material. This can be observed with the prism. Light traveling straight through the prism will continue in a straight line. If light enters the prism at an angle, the light will bend. The angle that light is traveling in relation to the media is called the angle of incidence. The greater the angle, the greater the bend. The refractive index of a medium is a number to specify how fast light will travel through it. For example, the refractive index of water is 1.333, meaning that light travels 1.333 times faster in a vacuum than in water. When light waves enter a medium such as water, prism, or air, it will bend. The refractive index determines how much the path of light is bent when entering the material. The greater the refractive index, the greater the bend. So there are two factors which influence how much light will bend when traveling through a transparent media: the angle of incidence and also the refractive index of the media. The total amount that light bends is called the angle of refraction. The atmosphere and air also refract light, just like water and a prism and a glass does. Light waves do not travel at the speed of light within the atmosphere, but light's velocity is continuously getting slower as light travels towards Earth through air which is continuously becoming more and more dense. A visualization of atmospheric pressure will help demonstrate this, as we know that air closer to Earth's surface is more dense than the air at the top of the atmosphere. So air high in the atmosphere, perhaps up in the exosphere, has a refractive index close to 1. But air near the surface of Earth has a much greater refractive index. This continuously changing refractive index causes light waves to follow a continuously curving path, as we know that light follows a curved path in a medium in which the refractive index changes. This is a study of the physics of the air and atmospheric refraction, which consists of three phenomena: astronomical refraction, terrestrial refraction, and a third and yet unaccounted for, horizontal refraction. Let's look at each one in detail. First, we'll consider a viewer on the surface of the Earth who's looking up into the sky at a celestial object, any star or planet, typically the sun. Because light must pass through the atmosphere and is continuously bent, astronomical objects appear higher in the sky than they are in reality. This is called astronomical refraction. When navigating at sea with only a chronometer and sextant, you can determine an accurate longitude and latitude by taking a sighting exactly at noon when the sun is directly overhead. The only time there is no visual distortion is when the sun is directly overhead at high noon, or your zenith. When the sun is at your zenith, the angle of incidence is 0 degrees, and that's why there's no visual distortion. The light from the sun is entering the atmosphere at an exact 90-degree angle to the atmosphere's normal plane. As the sun moves away from your zenith, the angle of incidence is increasing, and thus the amount that light bends will also increase. You can replicate the effect of astronomical refraction by looking at a specific marker on the ceiling, and view the same marker by looking through the bottom of a prism. If you cover one eye with the prism and one eye without, you will notice the marker is visible in 2 different locations. The research papers included in this video explain how to calculate astronomical refraction. Here we've done the math on paper by hand. Please study our work for correctness and accuracy and provide any feedback. The paper is included in the research documents and the links in the description. Next, we'll consider a viewer on the surface of the Earth who's looking into the distance at a terrestrial object, such as mountains in the distance or the visible horizon line. Another good example of this is when you're looking at a ship at sea and it's disappearing into the distance. The curving of light rays is not confined to those that come from some celestial object, but also applies to those that pass between any 2 points within the atmosphere. This phenomenon, known as terrestrial refraction, causes all objects on Earth or in the atmosphere to appear to be at greater altitudes than they actually are. Even initially horizontal rays normally curve down towards the surface of the Earth so that objects at the observer's own level, as well as those above or below it, appear elevated. To understand this phenomena, consider a light wave normal to the surface of the Earth and consequently moving horizontally. If now the density of air decreases with increased elevation, as it nearly always does, the upper portion of the wavefront will bend down towards the Earth faster than the lower, and the path will be bent down towards the Earth along a curve whose radius depends upon the rate of this density decrease. In this video from Skunk Bay, it's easy to see the effect of terrestrial refraction. Consider what this looks like from the side. A curve with a radius that's constantly changing. Notice how terrestrial refraction is responsible for a visible curvature on the horizon line, regardless if the Earth is a sphere or flat. As a common approximation, terrestrial refraction is considered as a constant bending of a ray of light or line of sight, in which the ray can be considered and described as a circular path. Once again, we've included the research papers which explain how to calculate terrestrial refraction. Please study our work for correctness and accuracy and provide any feedback in the comment section below. Let's now consider Newton's third law. For every action, there is an equal and opposite reaction. Considering there is strong visual distortion for the viewer on the surface of the Earth who's looking out through the atmosphere, and complicated mathematics are required to correct the distortion, What math formulas are then used to correct the visual distortion for the viewer who is outside of the atmosphere and looking back down to Earth? Wikipedia does not discuss this phenomena. Astronomical and terrestrial refraction are both instances where the viewer is on the surface of the Earth. Physicists do not discuss the phenomena. It's as if they assume that there's absolutely no visual distortion for the viewer outside of the atmosphere, which is a complete physics fallacy. Now, every time you've heard someone say, "The Earth is a sphere, haven't you seen pictures from space or from the ISS?" you can be sure they're assuming there is absolutely no visual distortion for the viewer in space. They certainly have never considered that mathematical formula must be applied to fix the distortion in the image they're referring to. So I'll ask you, the viewer, a question. Given astronomical and terrestrial refraction, what is the mathematical formula to correct visual distortion for the viewer who is outside of the atmosphere and looking back down to Earth? What effect does this have on the horizon line? If you have a serious answer, please comment below. Our research has led to a single truth. The horizon of Earth, when viewed from space, will suffer from visual distortion. The actual horizon and the apparent or visible horizon are not the same. Mathematical formula must be used to correct the distortion caused by the atmosphere so we know the true shape of the horizon line. Remember, there are two factors which influence how much light will bend when traveling through a transparent media. One, the angle of incidence, and two, the refractive index of the media. What is the angle of incidence for the viewer in space looking down to Earth? Their zenith, or high noon, the point where there is no visual distortion, exists directly in front of them. As you deviate away from this point, the angle of incidence is increasing. The same effect can be seen with astronomical refraction. At the viewer's true zenith, or high noon, there is no visual distortion. But the greater you deviate away from this point, the greater the distortion. And once again, you will find the point in the middle of the horizon to be the zenith, and as you deviate away from this point, the angle of incidence is increasing, and thus the image and horizon line is being distorted from its true location and altitude. Here's a diagram to explain angle of incidence. The normal is your zenith. When on Earth, this is the point in the sky directly above the observer, and when you're outside of the atmosphere looking back down to Earth, this is the point directly in front of the observer, the middle of their view. In astronomical refraction, the further a celestial object is located away from your zenith, the more its apparent altitude becomes distorted from its true location. Likewise, in horizontal refraction, the further a point on the horizon is located from your zenith, the more its apparent altitude becomes distorted from its true location. The visual distortion caused by the atmosphere causes the horizon to form a curve, with a specific radius of curvature determined by variables such as the viewer's altitude and the angle of the lens. Here, a 3D simulation shows the effect. A camera icon represents a human or camera lens. The math used for this simulation is included in the documents and is derived directly from the known data concerning atmospheric refraction. The higher up you are in the atmosphere, light must travel through more layers of atmosphere to reach your lens, and thus it will be refracted at a greater amount. This explains why altitude affects the horizon's apparent curvature. You can replicate the effect of horizontal refraction by looking at a perfectly flat line through a prism. I know this line on my ceiling is perfectly flat. However, when viewed through a prism, it takes the same exact shape as Earth from space. Why? Again, its angle of incidence. The light traveling through the prism directly in front of me is not distorted. It travels through in a straight line. But when a wave enters the prism at an angle, to the left or the right side, the wave will cross the boundary of the prism at different times. The greater the angle, the greater the difference in time when the left and the right side of the wave will change their speed. This causes the wave as a whole to change direction both when it enters the prism and when it exits. The further away you are from your zenith, the more the light is bent and the more the apparent altitude of the ceiling is distorted. To use a 1-inch prism which has a high refractive index, or hundreds of miles of Earth's atmosphere which has a low refractive index, is synonymous. In both cases, the same exact visual distortion will be seen due to light, refraction, and angle of incidence. The other major factor which affects the visible curvature is the angle of the lens in relation to the horizon line being viewed. Depending on the angle of the lens's x-axis, the horizon may be seen as concave, flat, or convex. In a traditional photo of Earth from space, the camera being tilted downwards towards Earth, you would absolutely see a convex-shaped horizon line. However, it's also possible to see a flat horizon line and also a concave horizon line. Now it's easy to understand why the horizon was reported as an upturned edge by Auguste Piccard in 1931. It's clear why Felix seen a concave, flat, and convex horizon even without a GoPro's barrel distortion. It also clarifies why the U-2 spy plane video at 80,000 feet witnessed a concave, flat, and convex horizon using a camera which has absolutely no barrel distortion and is rendering the image as the human eye would see it. So to the aviator who has been to 80,000 or 100,000 feet and says, "I've seen the curve," I absolutely believe you. Did you notice how the curvature changes with altitude and angle? Or did you spend most of the time looking down towards Earth and thus seeing a downturned edge?
And from this height, 67,500 feet, the edge of our planet has a definitive curve to it. It is more three-dimensional than I have ever seen it. There we are.
Did you subconsciously ignore the optical illusion you were seeing, which is caused by light bending, and just accept it at face value? The Earth is a sphere, because you went up and seen it? I doubt these questions have been seriously contemplated, even by NASA personnel. So the atmosphere distorts the shape of the horizon when viewed from space. What does this all mean? Well, the interesting part of this research project is that it unanimously confirms that when the camera's x-rotation is at 0 degrees and thus is normal to the horizon of Earth, the horizon appears to make a perfectly flat line. This can be observed in the included videos, which includes both GoPro cameras and also cameras with flat lenses and no barrel distortion. In summary, our research proves that visual distortion will be experienced for the human or camera lens outside of the atmosphere. When studying atmospheric refraction, you should not only consider astronomical and terrestrial refraction, but also the third and unaccounted for scenario, horizontal refraction, for when the viewer is outside of the atmosphere and looking back down to Earth's horizon. Our theory postulates that Earth's surface is perfectly flat and that the curvature seen from space is due to horizontal refraction. Likewise, when a viewer is on the surface of the Earth, the curvature is seen due to terrestrial refraction. And what about the movements of the stars and planets? Are they really moving, or is it just another optical illusion caused by the movements of light waves from a single light source? Given that light must travel on a circular path in order to reach your spherical eyeball, only to enter through a circular-shaped pupil, it's not surprising to see a plethora of circular-shaped objects that we assume are spheres in the sky above us. Documentation and research papers can be downloaded from the link in the description. You are allowed to download, share, repost, upload this video, and use it in any way you want to.